So as I mentioned, there's some relationships between the mean and the median that we're going to want to be aware of when we're describing quantitative data. So if your distribution is symmetrical, as we see here, then the mean and the median are going to be either be identical, which would be the case if it's perfectly symmetrical, or they're going to be very, very close. So here's an idealized symmetrical data set on the left, and you'll notice the mean and the median are both exactly equal to 16. In a case where your data set is right skewed, the mean ends up being higher than the median. So one way to understand that is, remember the median is the middle number, so if we sort of lined up all the data values, then in this case the median would be 6, which is here, whereas the mean would be 8.4, which is here, a little higher. And one of the reasons that's happening is because since most of the mass is over to the left, then when you're lining up the data, we should expect many more values sort of corresponding to the left side of the data set than on the right side. However, the right side of the data set has bigger numerical values, so when those get weighed into the calculation of the mean, they tend to they contribute a lot to that computation, which is sort of pulling the average up a little bit. Okay, so the median is generally going to be around where the center of the mass is on your histogram, whereas the mean will probably be slightly more toward the skewed side. And that again is confirmed over here on the right, the right-hand side. We see a left skewed distribution. In this case, the mean is lower than the median. So the median is here. Okay, that's our, I'll just use the word actually. That's our median. It's a little bit to the right of the mean. And again, that's because most of the mass is over on the right. So when you lined up all the data, most of the data is going to be in that area. However, there are some outliers over here on the left, and so when those get computed into the mean calculation, they're going to pull the average up. So that's a relationship you're going to either want to memorize or at least understand, because it has a few implications in terms of what we're going to want to report when we're describing a data set. So just as a little exercise, and again, I apologize for the poor granularity of this picture, but I just found this distribution on, it's probably Wikipedia. This is the distribution of annual household incomes in the United States from 2010. It's an estimate. Now the y-axis is a percent of households, so it's not actual counts. It's more like a relative frequency histogram. But in any case, we can say a few things. First of all, it's skewed right? We see a lot of mass over here on the left, and it sort of tapers off to the right. It might be considered bimodal because I've got two peaks, one peak way over here to the right. But the relationship I wanted to point out is where it says where might the median and the mean be in the distribution. And I guess I did notice that it's sort of given away here. But notice it says the median household income was $50,000, and that is right around here. So in this bar here, that's the median. Notice it's more towards the center of mass of this histogram, which in my mind means, makes sense, because most of the people make an income that's over here on the left-hand side. Fewer people make the incomes as you move to the right. I don't know, and we can't, without really getting into a crazy computation, we can't really find the mean here. But if we were to guess, based on what we learned in the previous slide, we should guess that the mean would be somewhere over here in this area, because you've got really rich people over here who make billions, and when they get computed into the average, or the calculation for the mean, they're going to have enough, they're going to be pulling that average up just by virtue of the fact that they're making an exorbitant amount of money. So we see in this case, we should anticipate that the mean income is going to be greater than the median. that has some implications in terms of how we describe this data set, because let's just say, for instance, that the mean ended up being, I don't know, like $100,000. That's misleading when you say, if you were, someone on CNN says, well, the mean income for people in the U.S. is $100,000. Does that really tell us that is the typical income? Is it really true that the typical income is $100,000 for people in the U.S.? Probably not, because most people make incomes that are over here on the left. And the mean is misleading because you have some really wealthy people who are pulling that average up. So that number is not something I would report in this case. The median is much more relevant. The median really tells you what the typical income is, and we're going to learn that the median is what's called resistant to outliers. And in the next example, we're going to do a calculation to really sort of get this concept to land. But again, it really does matter. It really does matter what your distribution looks like in terms of what you report for the center of the data. So one of the questions you're going to want to ask is, when should I report the mean and when should I report the median as describing the center of the data? Well, it basically has to do with whether or not the data is symmetric, okay? So let me just highlight a key insight that we've sort of touched upon. We say that the median is resistant to outliers. Okay, now resistant to outliers means that a big outlier does not necessarily change the median much, if at all. Okay, and that's important because sometimes we have data sets that have big outliers, and we want to be aware of how that can skew the information and skew the data. But the median is resistant to that, and that's because it only considers the order, right? It doesn't consider the actual values themselves. So, an outlier doesn't necessarily have an impact on the median. And I note that here. An exceptionally large or small value won't change the median. Won't change the median that much. I just noticed a typo here. Won't change the median that much, if at all. But it definitely will change the mean, as we're going to see. And outliers generally tend to cause distributions to be skewed, so we tend to rely on the median, and this is something I would highlight. We tend to rely on the median for skewed distributions, and we rely on the mean for symmetric ones. Okay? And again, I note we want to measure the tendency that best describes the center of the distribution, and the mean will do a better job for symmetric distributions, and the median will do a better job for again, another typo, skewed distributions. And I'm going to do an example with you, a simple example on the next slide to really reveal why this is the case. So let's look at a couple scenarios to distinguish between situations in which the mean is the appropriate number to report and when the median is. So I just have a few numbers here. These are incomes of 5 people came across. So go ahead and pause the video and find the mean. You don't need to do anything fancy. You just need to add up the numbers, divide by 5, and then I already put them in order. So the median we should see is just 42,000. So that we know. I'm going to pause the video and go ahead and find the mean yourself. Okay, so you should have found that the mean is 44,600. So the mean and the median are pretty close, right? They're not identical, but they're pretty close. So depending on what the distribution looks like overall, it might be fine to report either the mean or the median. But now let me extend this example here. So just imagine that Bill Gates' income gets added to the list. Now he's clearly an outlier. So his annual income, and I think this is somewhat credible. I might have got this from online. But his annual income is $3,710,000,000. So now let's find the mean and the median together. So let's first find the median. There's an even number of data values now, so the median is going to fall in between those two. It's going to be the average of those two numbers. Okay, and that ends up being 46,000. Okay, so I'm going to pause the video, go ahead and add these 6 numbers up and divide by how many there are, and then be ready to write down the mean. Okay, so what you should have got, or what I got, was, let's see, I got a 618,362,166.7. So what is that? That's $618 million about. So the question you want to ask yourself in a scenario like this is, are we really to believe that among these 6 people, like let's say you don't know anything about these 6 people, they're in a room, and I walk out and say, well, the mean income, the mean annual income for this group of 6 people is $618 million about. What does that tell you necessarily anything about those people in that room? Well, it really, depends. Not necessarily. It could be that they all, all 6 of them are very wealthy, and that is a number, that 618 million is a true representative of the data of those incomes. But as we've seen, it could be that you just have 5 sort of average people who make, moderate incomes, but then Bill Gates is also in the mix, and when he gets added to the mix, he completely distorts the mean. So it's not useful in this second scenario to use the mean. Okay, it's misleading. Remember, we want to talk about the center of the data as being what a typical income would be. And 618 million is not the typical income for these 6 people. In fact, nobody makes that income. No one makes even close. It's just that Bill Gates makes so much and all the others make so little that that's where the average ends up being. So let's just kind of indicate that here we would report the median for the center of the data. Okay, the median is much more telling, right? $46,000. That is a number that's describing the typical income for these 6 individuals. And again, the word typical because Bill Gates is an outlier. So we sort of want to almost ignore that his income because he's not typical. He is a special case. The median is revealing in a way that the mean is not in this case. In the above example, you sort of can use either. Again, you might need more information, but depending on the context, but either would probably be fine because you don't really have a value that's skewing the data. Okay, so again, just to highlight the point that we report the median when the data is skewed. And again, this is because it is resistant to outliers. It's resistant to outliers. And again, just to return to the point, if the histogram is symmetric, you'll use the mean. You'll use the mean because the mean is nice because it does take into account the values of all the data, right? So that's a good feature of it. It's just misleading when the data is skewed. But so we use it when the data is symmetric. When the data is skewed, we use the median.